Good morning, everyone. First, I guess I should apologize. I never got around, apparently, to updating the title on the program. So I'm not just going to try to cover all of quantum information theory, I guess. I went back, and in one of the very first emails, Christian suggested that I could talk about quantum differential privacy. So I figured I might do that. And there was basically two ways how this could go now if I talk about quantum differential privacy. One of them is I could tell you about like the very recent results where we kind of bound divergences, and it's all very technical and so on. But then I figured this might be a bit of a more general audience. So we might not want to deep dive too much into like individual inequalities and so on. So I figured I go for option 2, which is I give you a bit more of an overview. Where do I think this topic of quantum differential privacy is at the moment? And what are possibly the challenges that we should be looking at when we discuss this topic? Here you can see a whole bunch of people I've worked with on this topic over the last couple of years. And I should maybe say it turned out this talk is going to be a little bit more of like an opinion piece or something. So none of these actually have endorsed the talk. They just have like contributed to some of the results. So let me kind of start with the basic introduction and talk a bit about differential privacy as a concept. And of course, it makes most sense in understanding what we want to do if we start by talking about classical differential privacy. And where does this usually show up? So the typical problem is that you have some set of data, and the typical or the canonical example here is to look at medical data, for example. You think of a list of patients, and for these patients, you have done some tests, and these patients tested positive or negative, let's say, for a certain disease or like antibodies or whatever. And now you want to run some algorithm on it and publish a survey, let's say. Of course, if you publish a survey on medical data, sometimes you want to kind of convey as much information as you can, but you really want to make sure that somebody who reads the survey doesn't or isn't able to identify a particular test result of one of the patients on your initial data sheet, right? So that's a very natural problem. And the concept of differential privacy covers exactly that. So if you think of this data set and you're trying to compare it against the data set where exactly one entry has changed on this data set. So you switch one patient from a positive test to a negative test, then it should be almost impossible to distinguish this very small difference in the final result or the final printout of the survey that you did. Okay, so that's the basic premise. And now we kind of move to a quantum setting. So everything now becomes much more abstract in some way, because the goal is kind of to define this in a sensible way. And now our set of data is just a bunch of quantum states. The quantum states are like the different options. So you can think of these states as like the data sheets of lists of patients and tests and so on. And now you run some algorithm on it, after which you get output states, and these output states, they should be more or less indistinguishable if your data states were somehow close to each other. Okay, the typical thing that we define here is we call like two states neighboring states if they are by some relation close to each other. And we want now two neighboring states to be indistinguishable after a certain algorithm. Okay, so that's a high-level overview. And to get kind of the details out of the way, let's look at what this looks like when we formalize it. So you might not have to go through the whole text, but essentially we have like measurements, and we try to measure the outputs of the algorithm, and we get a probability, right? So far, so easy. Now, the probability for one neighboring state rho and the other one sigma should be very similar to each other up to some multiplicative constant, which is parameterized by this epsilon, and an additive constant. Okay, and if this is true, then they're naturally hard to distinguish in some sense. And we call this algorithm A to be an epsilon delta differentially private algorithm. Okay. For the rest of the talk, I'm going to use a slightly different version of writing down this problem. And it turns out that you can actually write the very same condition as a quantum divergence. Okay. So we have seen a lot of different talks and posters where we have introduced quantum divergences. So I'm not going to go into like the details, but essentially we have this, like, think of it like an analog to, like, I don't know, the trace distance or the relative entropy, just that we define this divergence, which is called the hockey stick divergence, E gamma. And it turns out that an algorithm is exactly epsilon delta differentially private if this hockey stick divergence for suitably chosen parameters is bounded by this delta for all neighboring states. Okay, so that's kind of just kind of the starting premise. And how to connect these two, it's not so difficult. You just have to see that this formula has like a variational expression, which exactly connects these measurements to this closed form expression. So I'm just kind of doing some rewriting. It will just make it easier for the rest of the talk to know that this differential privacy condition can be written as an information measure or like a divergence. Okay. So before we go ahead and talk a bit more about the details, I figured it's an overview talk, so it makes sense to talk a bit about the literature that is available about these things. So I'll start off with a bit of a timeline. And the whole topic of quantum differential privacy started off a little bit slow. So the classical differential privacy has been around for some time, but then of course, naturally, people see like a concept that's like heavily adopted and in the classical setting and has a lot of applications. So we start thinking about what is a quantum generalization of this concept and what makes sense in this point. And there's really, like, I would say kind of these three papers that kind of started this, and like always like a couple of years in between. The first paper that really mentioned differential privacy in the quantum setting was this paper on the top left by Zhu and Ying. And I actually get to the difference between these three papers a bit more in a while. But for now, I just kind of give you the quick rundown. They kind of introduced the version of differential privacy that you saw on the previous slide, not the divergence representation, but like the more straightforward generalization of the classical case. And they showed a lot of, let's say, applications in the context of quantum computing. Then the one that probably got a lot more attention was the paper by Scott Aronson and Rothblum, who now defined a different concept of quantum differential privacy. And here they talked about measurements themselves, not the quantum channels being differentially private. And there's a second important difference, which I talk about on the next slide. And then our work that came a couple years later kind of made these connections to these divergences, which actually gives you a much more convenient tool to work with this quantity compared to previous work. And kind of the following years, there's like a whole bunch of papers. Actually, I wanted to mention these two before. These two were kind of also 2022 papers that came up with like the first applications in the quantum computing area. The first one used particularly the Scott Aronson approach, and the second one by Du et al. Used the first approach by Zhu and Ying. After that, there's really a whole bunch of papers coming out that all somehow relate to this concept of differential privacy and really looked into how should we define this, how can we generalize it, and what are kind of the theoretical properties of this concept. And I kind of just want to point out two research groups. One is the one by well, Mark Wilde and mostly his back then PhD student, Tishani Nurada, who did a lot of work on quantum differential privacy over the last few years. And especially at this time, 2023, 2024, there's a group or the work led by Armando Agrisani, who also really did a lot of work on like narrowing down what should the framework actually be when we talk about quantum differential privacy. And this has kind of not stopped since then. So for example, some very recent work talks about like the privacy utility trade-offs of these differential privacy things. And even like Vasi and Hayashi and so on, Das Gupta, they kind of got interest in this recently as well and had some interesting results. So it's kind of just to show that this is still a very active field where even like the fundamentals of like, what does it actually mean to have this concept are kind of further explored. But to come a bit to like the things I mainly want to talk about, I'm going to take this list and going to reorder it a bit. Okay. Let's kind of take the starting point where quantum differential privacy was just introduced or like kind of formalized. And now you might realize there's one thing that I mentioned a couple of times, which I haven't explained at all, which is I want states, or I want these output states to be indistinguishable if the input states are neighbors, okay? Classically, they're neighbors, or two kind of strings, two databases are neighbors if they differ in exactly 1 bit. So now is the question, what is like the analog in the quantum setting if I want to define quantum differential privacy? And the first paper by Zhu and Ying, they actually just chose to define it as two states that are close in trace distance. Okay, that's now raises the question: what does it have? What does it have to do with the classical setting of differential privacy? And I'm afraid the answer is actually not much, right? It's like it's a generalization one can choose, but it doesn't reduce to the classical setting in any way. It's just kind of, that's what people think about when they maybe choose things to be close to each other. But it's a bit unclear, why would you choose this? There's a second definition by the Scott Aronson paper. And they choose what I would think is a intuitively much more natural definition. So now you think of your quantum states as being present on n systems, and two states are neighboring if there exists a local quantum channel that acts on only one of these n systems and transfers your state rho to a second state sigma. Okay, so now these rho and sigma are neighboring states. And now there's a third definition. If you're not familiar with the topic, you might be thinking I'm joking, but the third definition is they can just always be neighbors. Okay. That sounds like, okay, what does it even have to do with the concept in the first place? But it turns out that this is kind of a special case of this concept. So classically, people have to find something that's called local differential privacy. And in fact, there you don't look at kind of neighboring bit strings, but you just take input probability distributions, and any two input probability distributions are kind of are neighbors, okay? And that's kind of one of the main points I want to talk about on the next couple of slides, kind of justifying this concept in particular. So now I said I'm going to reorder the previous slide with all the papers. And essentially for each of the first two, there's like, I would say like two serious application papers, okay, that really think about like what can you do with this definition in practice. And I also mentioned this paper by Armando, who kind of thought about what would be a unified framework that takes both of these neighboring conditions into account. The first one is in the context, well, both in some way in the context of learning. The first one is kind of robustness against adversaries. And the second one is about statistical queries. And somehow in these contexts, they seem like natural definitions. But okay, especially the first one, the question is, why do we kind of call this differential privacy? But what's maybe the surprising part is if you look at this local differential privacy, there's actually a ton of applications of this. So people have looked at all kinds of information theoretic problems to see if it still holds under differential privacy. And it turns out that that is kind of a very natural way to looking at these things. Now, what do I mean with natural? Well, I kind of still have to convince you that it actually is a natural way of looking at these things. But there's also an argument to be made that this is just the version of differential privacy that's much easier to understand. So actually working with this mathematically is much easier than any of the other two conditions. So let's kind of deep dive a little bit more into this, the third definition first to understand this. And I want to kind of explain a bit where it's coming from, because maybe not so surprisingly, this also has like drawn some, I would say, like partially unjustified criticism. And I'm actually going to just call out Daniel and Ruben here, not because they're like alone in this opinion or something, simply because they're the only ones, I think, as far as I know, that dare to kind of write it down in a paper and put it on the archive. So they had a very nice paper, actually, where they talked about contraction coefficients, and in particular contraction coefficients, where you look at average decay and like data processing inequalities, right? And one thing they proved using these inequalities was that if you look at this local differential privacy concept, so where all states are neighboring, then it's essentially, on average, you would expect it's always hard to kind of distinguish the output states, okay? And that means, well, it sounds like that's what you want, but it also means that kind of computationally, anything you run through like these local differential private algorithms becomes kind of useless for computational purposes. And that's kind of the main criticism that people usually draw about this definition of local differential privacy. But I want to kind of give you an idea why this was classically introduced and why it's possibly a definition that is worth looking at in some way. On the left, so I kind of have the concept of like differential privacy again. So you have a bunch of inputs to your database. So people that provide you with data, then you have the data curator and who aggregates all the data and now sends it out in some differentially private way. So he does that usually by adding noise at the end of his aggregation of the data. Okay, and this is the concept of a trusted data curator. Now, what happens if you don't, oops, that was the wrong button. What happens if you don't trust the data curator? Now, maybe every single patient or every single data provider might be in a situation where they want to have privacy, okay? And at this point, the data they send you might be as simple as like a single patient file or something. So at that point, this general concept of like big databases at different one entry is not very useful anymore. And this is particularly the setting where in the classical world, people have introduced this local differential private concept. And to convince you a bit more that it's actually a natural definition, I want to talk about this a little bit in the quantum setting and put it in context with the second kind of natural definition of neighborhood for quantum states. Okay, so recall kind of in the Scott Aronson approach, we talked about differential, about neighboring states if they differ by like a local quantum channel. So let's kind of visualize that. And now I have a whole bunch of input states. So here you think of the individual patients as like individual quantum states. And what I do now is kind of restrict myself a little bit further. I really put them as like product states. Okay, so these are product states. And now, as you can see from the picture, also what I want is that each of them now experiences some noise, which doesn't have to be correlated. So I also here just choose product noise, right? And the outcome of this, I want to be differentially private. So what if I look at this now in the mathematical framework of this quantum differential privacy under the Scott-Aronson constraint? Well, if I have now quantum or input states that are neighboring, if they differ in exactly one of these systems, that's much less time than I thought I have. Okay. Then what do I want to say? Then it turns out that this whole quantity that we're trying to usually bound with some constant is actually just the single copy version of the differential privacy equality, simply because the quantity is additive when all the extra systems that I'm kind of taking away here are the same. Okay, so if the systems are identical, which they are, because I only allow difference in one particular bit or qubit. So this sample complexity, sorry, now I'm a little bit confused. This local differential privacy condition actually shows up very natural if I choose differential privacy and look at this Scott-Aronson kind of style neighboring condition, and just try to calculate that one. So actually local differential privacy is not like overly restrictive. It's just something that only applies in very particular settings. And in particular, like it's classically used, it applies in network settings and any settings where I have many copies available. So also there, it comes from, so when we apply it, for example, to sample complexities and so on, it's not so important that individual copies of these states become very hard to distinguish, but in a limit of large n, we expect a certain behavior, which is well modeled by this local differential privacy. And then I kind of wanted to talk about some more things, if you don't stop me. What kind of other things that can go wrong when I go from like classical differential privacy to quantum differential privacy? And there's one more thing which I feel like is completely missing when people talk about this concept. And that is naturally, we have entanglement as soon as I talk about quantum systems, right? And I could think about, for example, a setting where the states that I'm trying to distinguish, and which are in some form neighboring, have like reference systems that are also available to the person doing the discrimination task at the very end. Now, these reference systems shouldn't help the discriminator a priori. So what I do is I restrict them to be the same. There's different ways how one can look at this, but this is kind of one natural way of doing that that's motivated by like some contraction coefficient thoughts. So first of all, if I choose this reference system to be classical, this doesn't change the problem at all. So kind of a version with quantum differential privacy, with reference system is completely implied by a version without reference system. That's classically, and that's also the reason, of course, why classically nobody has ever bothered to add a reference system to this differential privacy condition. Now, if I go to the quantum settings, the question, is that still the case? Should I be worried about correlations with like some reference system or potentially even like an eavesdropper or something? And there are very simple examples that one can go through, like for example, a qubit depolarizing channel, which, okay, here, which I just give the definition here. And one can just check in the literature what kind of differential privacy this qubit depolarizing channel gives us. And it turns out now, if I allow for a reference system and I put in states that are indistinguishable solely on the reference system, still it violates like this differential privacy bound. So something that we didn't have in the classical setting now becomes very relevant in the quantum setting. And that is something that is very much kind of unexplored to how to define this properly when we take into account like correlations in systems when we look at these privacy conditions. Right, I have two applications in 1 minute. So I kind of just want to like drive home this point by like very quickly go over these two applications and kind of what I think should be the definitions of differential privacy that we should possibly look at. The first one is to combine the Scott-Aronson approach, which has been very unexplored in the literature somehow, of neighboring conditions with the addition of a reference system. And the reason is that we can prove properties that we are somehow not able to prove with the other combinations of properties, of definitions, but we can with this particular choice. So I'm just going to go over it, but the parallel composition theorem kind of tells me that if I take two epsilon delta differentially private algorithms, and the tensor product should also be like good differentially private. And that's something that's very clear classically, very simple to prove, but in the quantum setting, the usual definitions are not able to show that. So, or with the currently explored definitions are not able to show that. But if I choose this particular definition of quantum differential privacy, then it actually becomes something that is, I don't know, like a 2 or 3 line proof. So it's very easy to see. So that's kind of my argument why it might be worth it to look more at this combination. And the second one is that we should add this reference system to the local differential privacy condition, because that will allow us to look at a lot of applications that we had so far and lift them also from the application of quantum states to that of quantum channels. So I'm just gonna, since you're standing already, I'm just gonna say that we could look at the sample complexity of discriminating two quantum channels instead of, for example, states or similar things, and ask ourselves what happens if we add differentially private noise to these quantum channels, and can we still do that with like a reasonably good sample complexity. And we can do that for states, that's what we know from the literature. But if we just add this reference system, there's actually a very simple way how we can extend this now to quantum channel discrimination. And yeah, I guess I leave it with that. There are some takeaways which are basically about the things that I said, like that we should think about how we should actually define quantum differential privacy, and that we might have maneuvered ourselves a little bit into a roundabout or something with the way we are looking at things currently. And that there's a couple of things we should take care of when we make these definitions, and we should motivate them properly. And I guess I'll leave it with that. So you can. Thank you.
Thanks for your very nice presentation. So are there any questions?
Oh. Christoph, very nice talk, and I appreciate the overview of what's been happening in the differentially private world, which I really should follow more closely due to its relationship to covert communications and sensing. I have a question. So it's very clear that the local differential privacy is the strongest of them all. Obviously, local quantum differential privacy is the strongest, especially if you add the reference systems. The Scott-Aronson's view with the channel kind of acting as a ball, define a ball around some state, versus the trace distance or some other distance metric, I cannot quite see how they lie hierarchically. Is one stronger than the other in that if you show one, then it applies the other, or are they basically case dependent? Maybe that betrays my lack of knowledge of various quantities of bounds and all this stuff. I'm thinking that the data processing ability has something to do with that, and that by then you can probably make an error one way or the other. But what is your thought on that?
So I think in general, there are two like uncomparable definitions. Like if you specialize further, if you go to like product states or something, then you can relate them. But generally, they're just two very different definitions somehow. I would go as far as to say that if you choose this trace distance definition, you probably shouldn't call it differential privacy in the first place. It's like, classically, you have often this discussed concept of like stability of algorithms, which kind of replaces, like one of the ideas is to replace the hockey stick by like all kinds of other divergences and look at that. And there's some concepts which, where it makes sense to look at trace distance in the input, but like in the differential privacy context, it doesn't even reduce to classical differential privacy, right? So even in that setting, there are like very different definitions that don't have much to do with each other, actually. It's really kind of, if you have states that are already close in trace distance, then you make them even closer somehow. Like it's a stability concept. It's not so much differential privacy concept for me.
Right, it seems very similar to like the configuration theory approach. Can you try that?
I think, well, I mean, I know that some recent classical papers on like perturbation in terms of these, what is it called? Maximum leakage, kind of, which is very related to differential privacy. I don't think it's been very explored in the quantum setting. No. Thanks.
Maybe we have only 1 minute for one more question. Okay, so
let's thank the speaker again.